Okay, our next speaker will be Tınaz Ekim from Turkey. Tınaz visited us this year. She went to Poland as an invited speaker to our Gdańsk Graph Theory conference. She had a very nice talk during this conference. Tınaz came to Gdańsk with her children, and we were at the conference, and the son of Tınaz and my son, they spent very good time together. So Tınaz, please send greetings to your son from my son Simon. And we heard a very nice talk of Tınaz in the summer, and we decided to invite her once again to CARD. So we are very happy that you accepted our invitation. Tınaz works with graph theory topics, with some algorithmic graph theory and combinatorial optimization, things like that. But today she will talk about Ramsey theory problem, and the exact topic is theory and computation of the defective Ramsey numbers. Okay, Tınaz.
Thank you very much for the introduction and also for the invitation. It's a pleasure to talk to people all around the world, both Mexico and Poland and many other places. So here is my screen. Can you see it?
Yes.
All right. Yeah, and okay. So today I'm going to talk about defective Ramsey numbers, the theory and computation. So first some introductory definitions, and then I will talk about two approaches that we adopted to compute defective Ramsey numbers, considering these numbers in special graph classes and using efficient computer enumeration after trying all kinds of direct proof techniques, of course. And the results that I'm going to talk today are based on 6 of our previous papers. We've been working on this topic since 2013. With my co-author John Gimbel, most of these papers, and all the other co-authors are my former or current students. So if you are not familiar with Ramsey theory, don't be afraid. We're gonna go I will start very slowly, and it will not be a very technical talk, so hopefully everybody will be able to follow. Ramsey contributed to many different parts of science, like maths, economy, philosophy, decision theory, game theory, and but as he died very young, the person who really developed the Ramsey theory is Paul Erdős. And there's a very nice summary of Ramsey theory as follows. It says that one can find every mathematical object if searched in a large enough space. And there are applications of Ramsey theory in different fields of mathematics, including geometry, number theory, and of course, graph theory. And I'm sure you are all familiar with the famous party problem. So let's start with this party problem. There are 6 people waiting in the lobby of a hotel. Then the claim is that there are either 3 of them who know each other or 3 of them who do not know each other. Well, we can represent this problem using a graph where every person is represented with a vertex, and we put a red edge between 2 people knowing each other. And if 2 people do not know each other, then we put a blue edge between them. This gives us a graph, a complete graph actually, whose edges are colored either red or blue. And the claim says that as soon as we have 6 vertices or more, then there should be a red or a blue triangle. This is an example. Well, if you want to prove this, even for 6 vertices, if you use brute force, we have 15 edges to color, either red or blue each time. So there are too many possibilities to check. If you want to check, you can, and you will notice that each time you will be able to find a red triangle or a blue triangle, or both, actually. It's not exclusive. But of course, this is not a very clever way. So we rather try to show this without trying all possibilities and using pigeonhole principle. If you take one person, say Anne, Anne knows at least 3 of the other 5 people, or she doesn't know at least 3 of the other 5 people. It will be the symmetric case. So let's suppose she knows at least 3 of the 5 other people. Then the endpoints of these 3 red edges, right? If any 2 of these 3 people know each other, that will give us a red triangle. If none of them know each other, then these 3 people will form a blue triangle. And that's it. So this shows that the Ramsey number of order 3, is at most 6. Then the next question is 6 best possible? In other words, can we claim the same thing starting from 6 vertices? Well, the answer is no. Here is an example, which is a C5. If you just look at the red graph or just blue graph. So the statement does not hold for 5 people because there's at least one example where we don't have any monochromatic triangle. So this shows that the Ramsey number of order 3 is 6. Now, there are many, yes, and the formulation of the same claim in terms of graphs is that every graph, on 6 vertices or more contain either a clique on 3 vertices or an independent set on 3 vertices. Here, instead of coloring a complete graph, the edges of the complete graph with 2 colors, we focus on one graph and we talk about cliques or independent sets. Any questions so far? Okay.
Everything fine.
Okay, thank you. Well, there are lots of variants of the classical Ramsey numbers. The most known ones are the generalization of, maybe first the formal definition. The notation Rij means the minimum integer n such that all graphs with n vertices have either a clique of size I or an independent set of size j. And this is not exclusive, so we can have both. And this is the table of known Ramsey numbers. Only the green numbers are known for sure. For all the rest, we only have lower and upper bounds. And you can see that the difference between the known lower and upper bounds gets larger and larger. And there's a very famous quote by Paul Erdős about the difficulty of computing Ramsey numbers. Maybe you have heard about this. He said, imagine an alien force vastly more powerful than us landing on Earth and demanding the value of R55. Well, R55 is this one, so it's between 43 and 48. Or they will destroy our planet. In that case, we should marshal all our computers and all our mathematicians and attempt to find the value. But suppose instead they asked for R66, we should attempt to destroy the aliens. So we are all convinced that it's extremely difficult to compute any new Ramsey number in a near future, at least. Well, as I said, there are lots of variations of Ramsey numbers. in terms of number of colors that we use to color the edges of a complete graph, or Ramsey numbers for hypergraphs, graph Ramsey numbers where we search for not necessarily cliques and independent sets, but other small graphs, H and F, say. And our version here will be defective Ramsey numbers, where we generalize, in some sense, we relax the sets of vertices from cliques and independent sets to dense and sparse sets. So instead of cliques, we're going to talk about dense sets. And instead of independent sets, we're going to talk about sparse sets. How? Well, a set of vertices is called k-sparse if the graph induced by this set has maximum degree at most k. So when you look at the set of vertices and the graph induced by this set, the maximum degree is at most k. Of course, if k is 0, this is nothing but an independent set. So in that sense, we relax the notion of independent set. And k-dense is just defined in a similar way. Set D is k-dense if it induces a k-sparse graph in its complement. But maybe an easier way to think of a k-dense set is that it is close to a clique, except some missing edges, but we cannot have too many missing edges per vertex. So every vertex in D misses at most k others in D again. Here are some examples. Yes, and k-sparse and k-dense together, we call them k-defective. Here's a graph. Now, if you look at the set of vertices, the graph induced by yellow vertices, then, so the vertex 4, for instance, has degree 0. Vertex 18 has degree 1. Vertex 15 has degree 2, etc. And the maximum degree in here is 2 in the yellow graph. So this is a 2 sparse 11 set because there are 11 vertices. That's the number of vertices. Likewise, the green set here is 2 dense because for instance, the vertex 16 misses at exactly one other among the green vertices. And vertex 18 doesn't miss any other. And 17 misses 2. So every vertex misses at most 2 others in the set. So it's a 2 dense set. Okay, I hope the definitions are clear. Now, what do we know about defective Ramsey numbers? Well, we're going to define them in a similar way to classical Ramsey numbers. It will be the minimum integer n such that all graphs of order n contain either a k-dense I set or a k-sparse j set. Again, for k equals 0, we find back our classical Ramsey numbers. And we will be calling a graph extremal for a given Ramsey number rkij if this graph has order 1 less than the related Ramsey number, and it contains no k-dense I set nor k-sparse j set. So none of these forbidden structures in some sense. For instance, for the classical Ramsey number from the party problem, R33 equals 6, the C5 is an extremal graph for R33 equals 6. Now, by definition, a k-defective set is also k plus 1 defective. Just think of a k-sparse set. The maximum degree is at most k, and therefore at most k plus 1. So any k-defective set is also k plus 1 defective. Likewise, it's true for k-dense sets. It follows that the Ramsey number k plus 1 defective Ramsey number for parameters rj is less than or equal to the same, the Ramsey k-defective Ramsey number for the same parameters. And in particular, defective Ramsey numbers are less than or equal to the classical Ramsey numbers. Now, the first computation of defective Ramsey numbers are due to Cocaine and Meinhardt. Actually, by that time, they didn't call them defective Ramsey numbers, but one-dependent Ramsey numbers. And they compute these values using some direct proof techniques. Later, John Gimbel and I considered actually the defective co-coloring problem, which is the problem of partitioning the vertices of a graph using defective sets. So it is like the co-coloring, but defective version. And in that paper, we also showed that R255 equals 7. Later, Chappell and Gimbel published a paper where they studied asymptotics and exact values of various Ramsey numbers. The asymptotic behavior for diagonal Ramsey numbers is exponential, as you may guess. This is the same for classical Ramsey numbers. They also computed exact values using a computer enumeration and found all extremal graphs for defective Ramsey numbers having value less than or equal to 12. So this was the first time defective Ramsey numbers were considered in a systematic way. They also derived some bounds. So these are exact values, some upper and lower bounds on k-defective Ramsey numbers for parameters A and B, using k-defective Ramsey numbers for smaller parameters. So the first 3 are lower bounds and the last 2 are upper bounds. Later, actually, we published before this paper, but we used these results because we were aware of these results. John and Glenn kindly shared their draft with us. So with a student of mine, we used these lower and upper bounds to formulate, to form some tables for defective Ramsey numbers. So recursively computing best known lower bounds and upper bounds on RKIJ and putting this into a table. We also improved lower bounds whenever possible as follows. Just generate a random graph and check if it contains a k-dense I set or k-sparse J set. If not, well, then we know that the lower bound is one larger. So we just tried to find, by generating random graphs, a sub-extremal graph, I will call it, because we don't know if it is extremal, having no k-dense I set nor k-sparse J set to improve the lower bounds. And we obtained the following table for R1. Here, the numbers in bold correspond to the improved bounds using this technique of random graph generation. And we did the same for R2, R3, R4, R5, and so on. Well, we had almost no time limit restriction to enlarge these tables in terms of the parameters I, J, and K, because these upper and lower bounds can be very quickly computed in a recursive way. So we could go even further if we wanted to. But of course, the improvement algorithm, we had to stop it after 8 hours. And we obtained a total of 55 improvements, with the highest improvement being for R2 1010, which is by 9. But the most important outcome of this paper is that we couldn't obtain any new exact value. And this was expected, I think. But this shows, once again, that computing new exact values for defective Ramsey numbers is extremely difficult. So we need to take different approaches. And here, we went back to, okay, I called it a recent approach, but it's not anymore recent. It dates back to 2014 now. So in this paper, the authors considered the classical Ramsey numbers in restricted graph class. For example, let's go back to the party problem. R33 equals 6. And moreover, we know that the unique extremal graph is this 5 cycle. Now, let's consider the following question. What about bipartite graphs? What if we restrict the problem into bipartite graphs? Can we say that every bipartite graph on 6 or more vertices contain either a clique on 3 vertices, bipartite graphs do not have triangles, but, or an independent set of 3 vertices? Well, the answer is obviously yes, because this is true for all graphs, since the Ramsey number 33 is 6, and therefore for bipartite graphs in particular. But maybe then the next question, is 6 the best possible for bipartite graphs? Or does it also hold for 5 when we restrict the question to bipartite graphs? Well, the Ramsey number, classical 33, for bipartite graphs is 5. Because the unique extremal graph C5 is not bipartite. And therefore, every graph on 5 or more, every bipartite graph on 5 or more vertices contains contains an independent set of size 3. So here the question is it easier to compute a Ramsey number restricted to a graph class G or not? And in this paper, so what's your guess? Who likes graph classes? Any guess? Yeah, actually, it depends on the graph class. So there are 2 important results in this paper. First one says that if we restrict our attention to perfect graphs, then the Ramsey number in perfect graphs for parameters I and j is this: I minus 1 times j minus 1 plus 1. So there is a formula giving the Ramsey number for perfect graphs and also for any subclass of it containing all disjoint union of complete graphs. So yes, there are graph classes, at least one, for which it becomes easier to compute the Ramsey number. But the second important result is that Ramsey numbers restricted to Clos-free graphs, or so independently AT-free graphs, or the class of PL-free graphs, are at least as difficult as determining Ramsey numbers for arbitrary graphs. So actually they show that they are equal to the classical Ramsey numbers in general graphs for these graph classes. So it's not any easier. Well, for defective Ramsey numbers, we decided to take this approach of considering Ramsey numbers, defective Ramsey numbers in various graph classes. Now the definition is as follows. So the notation RKGIJ. This is the minimum integer n such that all graphs in this given graph class G of order n or more contain either a k-dense I set or a k-sparse J set. And an extremal graph is defined as before, but this time it also has to belong to the desired graph class G. And as previously, we observed for the classical Ramsey numbers, the defective Ramsey number restricted to a graph class G is bounded above by the k-defective Ramsey number in general for the same parameters. So just think of the bipartite case in the party problem. Okay, we first considered perfect graphs and small one defective Ramsey numbers in perfect graphs. Well, we have these numbers that we obtained using some direct proof techniques, where we basically consider the neighborhood of specific vertices. And their degree can help. Actually, we can restrict the degrees sometimes. And we basically use the structural properties of perfect graphs, no odd holes or odd anti-holes. And that's it. And at the end of this paper, we computed one value, R155 in perfect graphs, which is 13, using a computer-assisted proof. What we did is the following. We took all perfect graphs of order 9. So this list of all perfect graphs of order 9 is provided by McKay in his, it's available online on his webpage. And then we added one new vertex in all possible ways. Then check if the new graph contains a one defective 5 set. If not, we check if it is perfect. We store such graphs and we add one more vertex in the same way and make the similar checks until we get 13 vertices. And we could see that we have, so for all perfect graphs with 13 vertices, all perfect graphs with 13 vertices, we have either a one defective 5, one sparse 5 set or a one dense 5 set. Okay, so this was the beginning of computer-assisted proofs, but we continued later on taking a more systematic approach. In between, we also computed several exact values for defective Ramsey numbers in different graph classes, namely for forests and for cographs. Nicely enough, we could obtain a unique formula giving the defective Ramsey numbers for all parameters k, I, j in forests and cographs. For other graph classes, okay, this is the summary of what we obtained in that paper. So each color, yellow, green, and blue, correspond to a graph class. Yellow, cactus graphs, green, bipartite, and blue, split graphs. And the columns correspond to different conditions on I and j, and then k equals 1, 2, 3, or at least 4. Well, in most of the cases, we could find formula giving the related defective Ramsey number. There are a few open cases, like for cactus graphs, for k greater than 4, and I equals k plus 3, and j larger than 2k plus 2, etc. For bipartite graphs, again, an open case here, and a few numbers that we couldn't compute, but we conjectured that it is 2j minus 1 as the following values here. And also for split graphs, for the open case, we have a conjecture. And this was basically the end of our attempts to obtain exact values or formulas for defective Ramsey numbers in graph classes. Then we said, okay, now it's time to consider computer enumeration in a more systematic way. Note that in order to show that a given for given parameters k, I, j in a given graph class G, to show that the Ramsey number is n, we need to do two things. First, show that all graphs of order n in that graph class has a k-dense I set or a k-sparse J set. And note that by definition, a Ramsey number is a minimum n satisfying this. So we need to show that there is at least one extremal graph. So at least one extremal graph of order 1 less, again belonging to the same graph class, having none of these forbidden structures, let's say k-dense I set nor k-sparse J set. From a computational point of view, there is a big problem here. I guess you can see it. The number of graphs of order n grows very fast. So there's a huge number of graphs of order n. This is the number of non-isomorphic graphs of order 11. And even if we restrict to a given graph class, say perfect graphs, there are not much less. I mean, there are less, but it doesn't help much, let's say, because there are still too much to check. Note that we need to take all these graphs and check whether they contain a k-defective set or not of size I and j respectively, right? Well, we cannot really do that. We should find a way to enumerate these graphs in a more efficient way, namely without generating all of them and then checking whether they contain these forbidden structures or not. We should be able to eliminate those graphs at earlier stages of their generation. Otherwise, we will have too many graphs to check. And of course, there's this huge problem of checking isomorphism, right? It's very hard to check. And the best known isomorphism check algorithm is NOTI by McCain and Piperno. And that's the one we used in our implementation. Okay. So having these difficulties in mind, we suggest the following algorithm that we use for different graph classes. So I give the generic form now. Actually, this algorithm aims to find extremal graphs. And before we know the size, the related Ramsey number, we will talk about sub-extremal graphs. So those graphs not containing the forbidden structures, but we don't know if this is it has the size of an extremal graph or not yet. So it will start with a given set of graphs on, say, n vertices, which has none of these structures. No k-dense I set, nor k-sparse J set. And the output will be all graphs on one more vertices. So the idea is to start with just one vertex at the beginning, n equals 1, and then use this algorithm iteratively, taking the output of one iteration as the input of the next. So we will get graphs which are larger and larger. So the output at every iteration will be all graphs on one more vertices belonging to the desired graph class, which should be part of the input as well, of course, which has no k-dense I set nor k-sparse J set, and containing at least one graph from the input graph as an induced subgraph. Okay, so here's how we proceed. For each graph in the input set, we construct a new graph that we call GS by adding a new vertex V in every possible way. Then just examine all subsets of the new graph containing V. This V I will explain later. And eliminate those containing a k-dense I set or a k-sparse J set, because I want to obtain extremal graphs, those not containing these forbidden structures. So if a graph contains, even if it is small, if it contains a k-dense I set or a k-sparse J set, any graph that I will obtain later by adding new vertices to this, will also contain these structures. So I can get rid of it at early stages. I will only keep those not containing the forbidden structures. And then at those graphs belonging to the desired graph class, so I will check whether it belongs to the desired graph class among the remaining ones. And at the end, check isomorphism to return a maximal set of non-isomorphic sub-extremal graphs. And here is, of course, key concepts, how we implement adding a new vertex in every possible way, then checking all subsets of the new graph of size I and j, respectively. But of course, if the input graph is good in the sense that it doesn't contain the forbidden structures, then we only need to check those subsets containing the newly added vertex to check whether the new vertex created one of those forbidden structures. And also, we need to make some recognition for the given graph class, whether the new graph belongs to the set or not. Well, how we use this algorithm? We start with an isolated vertex and apply the algorithm in a repetitive way by taking the output set of one iteration as the input set for the next iteration. And we stop when the output set is empty. That means that the Ramsey number we are searching for is n+1, where n is the order of graphs in the last input set. And this last input set is the set of all extremal graphs with n vertices for this Ramsey number. And as I said, the input graphs at earlier iterations, we call them sub-extremal because they don't necessarily have the maximum possible size, but they are candidates somehow. Okay, the efficiency of this algorithm depends on how we perform the recognition algorithm for various graph classes. And here we need to take advantage of the structural properties and characterizations of graph classes. I'm going to give a couple of examples where we can even skip this recognition phase if we have nice structural results which allow us to, when we add a new vertex, generate only those graphs belonging to the class. So that will be an example, the case for cordon graphs, for instance. And also, we should use the fact that the new graph, after adding the new vertex, V, is obtained from the previous graph by adding one vertex. So it will be enough to check subsets containing this new vertex, as I said. In all our computations, the isomorphism checks are the most time-consuming part as compared to the perfectness or graph recognition in general and forbidden K defective set checks. Okay, for perfect graphs, what did we obtain? Well, perfect graph recognition is polynomial, but highly polynomial. So instead, we used an exponential time algorithm based on strong perfect graph theorem, which says that a graph is perfect if and only if it contains no odd holes nor complements. So we basically check this in an exhaustive way. And we could compute new values with respect to the previous ones, let's say, as follows. So these two values are obtained as a combination of computer enumeration, which yielded a few sub-extremal graphs that we later used to develop our proof using direct proof techniques. And in general, we could obtain all defective Ramsey numbers with value less than or equal to 15, each one in less than 4 hours. Note that McKay gives the list of all non-isomorphic perfect graphs up to 11 vertices only. So it would have been impossible from a practical point of view to take all these perfect graphs on 11 vertices, plus check them for forbidden defective sets subsets and add one more vertices, etc. Okay. These are the tables that we obtained for perfect graphs. Actually, the bold numbers correspond to the newly computed numbers, like 7, 8 here, in addition to previous formulas. And the numbers in parentheses are the numbers of extremal graphs that we could obtain with our algorithm. Yes, this is what we could obtain for perfect graphs. Then we also applied this idea to bipartite graphs and chordal graphs. Well, for bipartite graphs, the recognition is very efficient. So we could obtain tables for our 2, 3, and 4 with values less than or equal to 15, each value in less than 5 minutes. We could go further, actually. But here, I would like to talk about our formulas. If you remember the colored tables, we had a row for bipartite graphs and a conjecture for R1 for j equals 2j minus 1 for the values of j in this set. Well, we have conjectured this, and our computations show that this is false for j equals 10 and 11. So we could obtain these two values, 18 and 20, sorry, which does not follow the claim. So our computations show that the conjecture doesn't hold. But we couldn't compute the related Ramsey number for 12, 18, and 19. Then we moved on to chordal graphs. If you know chordal graphs, they are very nice. And in particular, a graph is chordal if and only if it admits an ordering of its vertices called perfect elimination ordering, such that for every I, the neighborhood of the vertex in order I here, its neighborhood in the upcoming vertices is a clique. So take a vertex, look at its upcoming neighbors, it should form a clique. And there is such an ordering of the vertices if the graph is chordal. So we could use this property, this characterization, in a to make our algorithm more efficient. We did not add a new vertex in all possible combinations, but we added a new vertex that we made adjacent to all possible cliques. In other words, the new vertex will be, so we put it somewhere in the perfect elimination ordering. And in this way, we know that what we obtain is a chordal graph. Moreover, we can obtain all chordal graphs in this way because it's a characterization. And this allowed us to skip the chordal graph recognition step, which in turn allowed us to obtain tables for 2, 3, and 4 defective Ramsey numbers in chordal graphs with values less than or equal to 20 and each value in less than 12 hours. And values less than or equal to 15 in less than 5 hours. Note that again, if we have used the list of all chordal graphs provided by McKay for up to 13 vertices, we will not be able to compute these Ramsey numbers. So the idea is to eliminate those graphs that we know it will contain one of the structures that we are looking for at some earlier stages. We get rid of it and all the graphs that will contain it. Okay, and lastly, we applied this idea to triangle-free graphs. So this is the last paper. Well, for triangle-free graphs, There's no triangle, so no clique of order 3 or more. And actually, we can generalize this to dense sets. There's no triangle, and this implies that there's no k-dense I set for any I greater than or equal to 2k plus 3. So there's no point of looking at k-dense sets of high order. This helps us to restrict our attention to some Ramsey numbers where the clique size is actually less than or equal to 2k plus 2, because after this, they're all the same for the same k and j, of course. Okay, here I used this small triangle superscript to denote triangle-free graphs. So we're going to compute Ramsey k-defective Ramsey numbers in triangle-free graphs for all i's between k plus 2 and 2k plus 2. And more generally, in triangle-free graphs, since there's no large k-dense sets, we are rather interested in k-sparse sets. So we also introduced a new parameter, which is the minimum integer n, such that every triangle-free graph of order n has a k-sparse j set. Well, actually, this corresponds to the Ramsey number 3j for k equals 0. Since there is no triangle, right? We think it makes sense to focus on sparse sets in triangle-free graphs. So we're gonna compute these t parameters instead of the Ramsey numbers using the same algorithm, where we're gonna skip the dense subset checks. Okay. Well, in direct proofs, the main tools are a lower bound, on the k sparse, the size of a largest k sparse set. So this is just a generalization of the lower bound on independent sets for triangle-free graphs, and also the fact that the maximum degree is bounded. It cannot be very high because the neighborhood of a vertex in a triangle-free graph is an independent set, right? So this helps us to obtain desired sparse set. Okay, in our computer enumeration, we used parallel implementation for both the graph generation and isomorphism checks. And adding a new vertex to every possible independent set in the previous graph generates all triangle-free graphs. So we could obtain all the numbers up to 18, each one in less than 2.5 hours. And this is the table. And here I'm going to conclude with some interesting remarks about what we obtained. Well, if you fix k, look at k equals 6, for instance, this arrow. Then we see that for I between 2 and k, tk k plus I is equal to this. In other words, it is increased by 2. 9, 11, 13, 15, 18, 17, etc. Well, in terms of tkj, this means that we have all tkj values where j is between k plus 2 and 2k. And in particular, for a fixed k, there are k minus 1 values, all these colored values here, that grow linearly. This is pretty interesting because this is not a usual trend for Ramsey numbers. And we know that this trend doesn't continue for large numbers. Like the growth rate of tkn is the order of n squared over log n for a fixed k. So this is an interesting trend. And so this is from computation to conjecture. so we conjectured that this trend continues. So for all the values that we could obtain with our algorithm, it is supported. And we conjecture that it continues for the rest. And actually, now from computation to conjecture, and then from conjecture to theorem, we could show this for the red diagonal, so I equals 2, and then for the yellow diagonal and the blue diagonal. So these are now theorems, not conjecture. But the same way we prove these theorems cannot go forever for larger I values. And one more thing which is interesting here is the number of extremal graphs. Surprisingly, in all these diagonals, you see in parentheses 1, and then in yellow it's 2, in blue it's 7, in green it's 46, a strange number, which repeats all the time. This is also a very regular trend, which is quite surprising in Ramsey theory. Okay, my conclusion here is that there are several research directions arising from these works. Well, there's a very nice interaction between computer enumeration and classical proof techniques. Computing new values can refute some conjectures, as it was the case for our bipartite graphs. And sometimes you can recognize some pattern in the computed defective Ramsey numbers, which can turn into conjectures and then hopefully to theorems. And also these patterns in the structure of extremal graphs can be sometimes generalized for larger parameters and provide us lower bounds for large, so a general lower bound for any defective Ramsey number, if we can generalize it. Okay, that's pretty much what I want to say. Oh, yes, maybe last thing, efficient enumeration for graph classes. This is at the heart of our generic algorithm. Recognition, it's not a good idea to recognize, so generate every possible graph and then check if it belongs to the given class. It's much better if we can efficiently enumerate all graphs belonging to the desired graph class and do this exhaustively, of course. So we should generate all graphs of given order belonging to the class, but do this in an efficient way. Okay, thank you for your time. And if you have questions, I'm ready. Sorry if I took too much time.
Okay, Tınaz, thanks a lot for approaching us this quite difficult and theoretical problem in such a nice way. Are there any questions here or on YouTube? No questions.
Okay, maybe it was a bit long and you are all tired.
Oh, it's early for us. Okay.
Only for you.
Don't worry. No. I think this is a topic that is always difficult. Not difficult, it's very surprises. Again, the difference between some numbers, some problems that look very easy, the case, for example, that is okay. And then start to be more and more complicated. And I don't know, it's very interesting, this last result that you have of this number that is repeat the number of extremal graph. And that is 1740.
Yeah, it's very surprising. Why? I've never seen such a trend in Ramsey numbers. It's too regular. There should be something in here.
Yes, yes, it's very, very strange. Very interesting. So,
Okay, thank you very much. And
thank you of you. Like that.